All right, so, okay, well, it's sparse. Yeah, I didn't prepare the important concepts today, but I'll make some after the course and put them on the site as always. But they're really, it's just a couple. Uh, So maybe just verbally, let me say, the two things we want to really understand today are going to be, what does it mean? What does the curl of a vector field mean? And Stokes theorem. That's what we're going to cover, those two things. Okay, a couple of housekeeping items. On the syllabus online that you have the final exam rooms, I'm going to send an announcement later today. Just with the final exam rooms, they are different than the regular hourly exams. So please do check that announcement. There's only 2 rooms, I believe, so it'll depend on who your recitation instructor is. I haven't gotten that many requests for alternative times. I'd like those to get into me by, let's say, Thursday morning. I will send an announcement requesting that from everybody. So if you know about needing an alternative time, I'd like to hear from you within the next couple of days so we can make those arrangements. For the students that work with the Student Access Center, you'll receive an email from me if I have letters from you. We do have a room available for them, and that's all planned out as well. So you will be hearing from me this week about those things. I also have a course review online, probably Zoom, on Monday, I'm thinking, next week. I'll make the announcement Thursday. If people can't make it, I will have some availability Monday and Tuesday next week. So people should, well, send me some emails when you receive that announcement if you can't make it and would like to have an alternative session. I'll give up some extra time, some extra office hours to go over. And finally, there is a practice written final that is on the website that you can check and work through your solutions. So yeah, please take a look at that. That'll help give you an idea of what types of questions you should expect on the final exam. Okay. All that said, let's do this these last couple of sections. Very important. It's really, I mean, as I've lamented before, it's very sad to only have 2 lectures per week, because we're really in this last few weeks getting to some of the most interesting results in mathematics that is really in this course. So hopefully you're with me and we can explore these great ideas. So let's just do a quick review what we've done, what we've defined in the last few weeks. So what we're really interested in is we were interested in expanding sort of 2 parts of our integral, the space part and the integrand, which is whatever we're integrating. And we did that. We talked about spaces, space being either a curve or a surface in our case, but there are more general cases too. And we talked about oriented spaces. This was the generalization of the domain. So an oriented curve, oriented surface. Let's just say OC, OS. And to these new kind of spaces that we're considering, we consider different integrands. If we just had a space, we talked about a scalar integral. But if we had an oriented space, we could talk about a vector integral. which really was built off of the scalar integral. But certainly the idea here is that what we're integrating is a scalar function. So this is a scalar function. And then we also had a vector field. So we've accomplished this much. This is as far as we go in this course with the generalization of our integrals. But then we did have some things we wanted to say about these new things. So we didn't want to just say, okay, well, here's some integral. We want to say, well, there's some theorems that we have. And the main sort of mega theorem that sort of guided as our sort of template for all of the theorems was this generalized Stokes theorem. You can think of it as a generalized fundamental theorem of calculus. And I wrote it in this form that mathematicians write it, but we have to make sense of it in our course in all these different cases we're considering. So we had a few examples of this. We've had the fundamental theorem of line integrals and the fundamental theorem of calculus. And we had a Green's theorem that we've talked about. In the last two lectures, we have two more theorems. So this generalized is often dropped by mathematicians, but it really is a more general version of a classical theorem called Stokes theorem, which we'll talk about today. So we want to when we go through how we can take this template and apply it to a particular case, we need to identify all of the symbols here. So in particular, we needed to identify, say, this domain D. And for the Stokes theorem, the classical Stokes theorem, D is going to be a surface. And that may lead you to ask, okay, well, hold on a second. I just kind of lied, actually. Not quite a surface, it's an oriented surface. So now that I've written that, that might lead you to ask the following question. It's a good question. What about the boundary? Certainly we know what the boundary of D should be. It should just be some curve that's on the boundary of D. If we draw a picture. And my surface is it's like this, some ridges or something. So some surface. So I know that the boundary is this region up here. But what I want to say is that this boundary that I'm going to get is also going to be an oriented curve. And we talked, when we were talking about Green's theorem, about compatibly orienting a boundary with a region in R2. However, we're not in R2. We have a surface now in R3 in 3 dimensions. So we need to be a little more thoughtful, I say, about what does it mean to compatibly orient the boundary of a surface if it's a surface in R3. And for that, we have to use the orientation of the surface. So this being an oriented surface means that at each point here on the surface, we have a vector, a normal vector, say a unit normal vector. It's continuously varying. If we head out to the boundary, we can kind of take that unit normal vector and we'll get a unit normal vector in the boundary. Now this vector is not tangent to the boundary. So it doesn't give us an orientation of the boundary per se. It just gives us some normal vectors. So this is not our orientation. But what it does is it allows us to put a person on the boundary. I don't know. Jay-Z or someone. Right? Here's a person. We have a normal vector. We can orient the person as far as where their head goes. Their head goes pointing up. And if we do that, now we're on the boundary. I'm a person on the boundary. And I have a notion of what's going to be on my left and my right if I walk along the boundary. And we know what Beyonce says. She says it should be on our left. So we do that. If we walk this way with our head facing that direction, the normal direction, then we know that our surface is on the left. But we do need to orient our head before we can figure out what our left and right is. If we were going the opposite way, our orientation would be going the opposite way. So this is the notion. I'm not going to write that out in words because it's just a lot of words. Hopefully the picture is clear. Are there questions? Is the picture clear? Do people understand how one would compatibly orient the boundary? So in this case, if I have my domain D as my oriented surface, then when I talk about the boundary, I mean it's the oriented curve with orientation that's compatible with the orientation of the surface. Okay, so this is this picture. There is, of course, a non-drawing stick figure way of defining all of this, but it's takes some time, and I'd rather not get swallowed in those details. Okay, so now we've taken care of how we're going to generalize these guys, but there is this other ingredient. Of course, there's eta, and eta in our case is going to be a vector field. So these are both going to be vector integrals. And it's a vector field in 3 dimensions. This is a very 3-dimensional theorem, the classical Stokes theorem. But there's another ingredient that's missing that we needed to find in all these cases, and that's this lowercase d. And what is this? This should be some kind of derivative, some type of derivative. And for that, we do need a new notion, or at least a definition. So as I said, eta is going to be a vector field in 3 dimensions. So let's give ourselves some notation for that. Let's suppose we have a vector field. I'll write the components P, Q, and R. And I'm just going to say vector field. I mean, it's going to be differentiable, but okay. I'm going to leave off some of these conditions in the interest of brevity. Then we can define the curl of F to be the following vector field. It's going to be Ry minus Qz, Pz minus Rx, Qx minus Py. Where of course the subscripts mean partial derivative with respect to that variable. Another way of writing this, or of computing this, say, or remembering this, which I think is probably the way you should try to remember this, because you're not, oftentimes, this formula is not going to be very helpful. Sure, you can look at it and do it, but if you wanted to kind of remember it, this is probably a better way. You take your partials and you view your partials as being sort of like entries of a vector, free vector. And you can do this kind of a business. If you look at the second row, here I'm taking determinant. Look at the second row of this 3x3 matrix. That is sort of like nabla. Nabla being this operator that gives you gradient. Del x, del y, del z. And that's what motivates the following alternative notation for curl, which is you take nabla, take cross product with F. course, nabla is not like a set of, it's not a vector field. It's not a bunch of functions. It's a bunch of operators. But the point is that algebra here is the same. The computation is basically the same. But you can just take this as notation if you want. Now, one thing to notice. So first thing to note, curl takes as inputs vector fields, and it outputs vector fields. It's the only sort of derivative we have in this course that really does that. The gradient takes in a scalar function and gives a vector field. It doesn't take a vector field and give a vector. So the curl is sort of unique in this way. And that's an important thing to remember when you're doing computations, because you don't want to get turned around on what you're doing when. What is your input? What's your output? Another interesting thing to look at is to ask yourself, what is the curl telling us? Have we seen this before? Let me turn it to you guys. Have you seen this before in some way? Is it evoking pleasant memories, horrifying memories, no memories? Is there anything familiar at all about it? I hear whispering. Yeah, someone said conservative vector field test. It looks a little bit like this, right? This is called the cross partial test, right? If I wrote this, right, that was the cross partial test. Well, one way of writing that is to say something like that equals 0. This is this cross partials test. In other words, if I take a vector field, take its curl, and observe that it's actually the 0 vector field, then F satisfies cross partial test. And so this gentleman said, gave different words for this test. One collection of vector fields that we know satisfy the cross partial test are conservative vector fields. So this is true if and only if, and not just then, if and only if. Sorry, do you guys know that? If and only if. So in particular, what I'm saying is that if I take the curl of a conservative vector field, say I have a potential, this is 0. That's a good thing to keep in mind. It gives you a new way of seeing certain phenomena, as we'll see in a moment. But before we get to that, let's just do a basic problem and see what we can say. Here's a problem. Let's compute the curl of a vector field. Say F equaling minus Y, X, C. Okay. I've forgotten the formula, even though it's written above and still on the screen. I've completely forgotten it. So instead of using that formula, I'm going to remember what I can definitely remember, and which will be, again, more effective than looking at a formula. I think it will actually minimize your mistakes. Just write this out. a determinant. Now, when I want to calculate the x component, I look at this 2 by 2 matrix and take the determinant, which means I apply the derivative with respect to y of z, that's 0, minus the derivative with respect to z of x, which is also 0. So that's just 0. I then cross off these two for the y component and take the determinant of that remaining 2 by 2 matrix. And determinant, again, is loosely interpreted here because we're really taking derivatives, but it's the same formula as the point. So we'll take the derivative of z with respect to x, that's 0. The derivative of y, negative y with respect to z, that's also 0. So I get 0 here. So far, so good. Last component, I have to cross off this row and column, take the determinant of this. Now I get some non-zero things. I get the derivative of x with respect to x, that's 1, minus negative the derivative of y with respect to y, which is also plus 1 once the negatives cancel. So I get 2. So I get this guy. All right. So it's not any, I mean, okay, so some of the vector fields will have more complicated functions, but the derivatives are not any harder. It's just taking partial derivatives. So going back up here and remembering what we're headed towards here, is we want this classical Stokes theorem. We identified the domain. I've identified what eta is. And now we're going to finally identify D as the curl, lowercase d. And with these in mind, we can write down the classical Stokes theorem. So let's let F, I want to use F actually, not a fan. I'm going to write A. Let A be a differentiable vector field. Meaning all the components are differentiable in R3, 3 space. S, an oriented surface. With compatibly oriented boundary. We'll call it C. Then the vector surface integral of curl of A yes over our surface is actually equal to the vector's line integral over the boundary of A itself. And I put the circle there because, of course, boundaries of surfaces. Our surfaces will be bounded. They're not going to go off to infinity. So the boundaries will be closed curves. All right. Now, there is a case, we've seen this before. It's worth noting. If S is a region in the XY plane, so we have this picture here. And our region is, this is our surface, say, S. Well, if we want to make it oriented, we can give it an orientation by orienting it with K. So let's just take K as the orientation. I'll put it over here. But, of course, you can think of it as just, it's at every point, it gives us a smooth normal vector, or it gives us a normal vector at every point. So if we orient it that way, then we can say, okay, well, if we look at Stokes theorem in this case, then we'll get the following thing. We'll get, if our curve C is, so S I'll call D because it's a domain in the plane. C is going to be the boundary of D. And I'm going to take the integral over the boundary of D of A. This is the right-hand side of Stokes theorem. And this should equal the surface integral here, S over S of curl A dot ds. But this is equal, by definition of surface integrals that we gave last lecture. And now I'll use my notation D to the curl of A, which is a vector field. I'm just not going to write the whole formula out. Dot the normal vector, the unit normal vector, which is K in this case. ds, the scalar integral. That's the definition of the surface. Normally, we don't have a constant normal vector. It has to change. But in this case, it is. But if I dot with K, a vector with K, what I'm really doing is I'm just pulling out that last component. I'm dotting with 0, 0, 1. So I just get that last component. And so what this is the integral over D of the last component, which if you look above, it's going to be Qx minus Py. And ds now is just dx dy, or dA if you want. Different A, it's called dx dy. And this equality is Green's theorem. It's the theorem in the plane. So Stokes theorem is really just it really does generalize Green's theorem. But more accurately, Green's theorem is used to prove Stokes theorem. You can actually use, if you wanted to actually prove Stokes theorem, the way to do it is to use Green's theorem. Okay, just wanted to make that relationship clear. All right, let's do a problem. Again, I'll give myself something kind of simple to work with, relatively simple. Let's see if we can understand it. So let's problem. Let's let K again be the unit. We're going to say the constant vector field. Which is just 0, 0, 1. But we'll think of it as a vector field. So every point gets assigned K. Let's let S be the following surface. S is the surface 3 plus z squared equals x squared plus y squared. And we're going to bound it. So we'll say with z, absolute value of z less than equal. And we'll orient it. Oriented outward from the origin. Okay, let's compute a vector surface integral. We'll take our vector field K, and we'll compute that. Solution. Well, last lecture, we learned how to do this. We learned how to compute vector surface integrals. and it was not the most pleasant experience. Well, I don't know, maybe some of you like it. It's difficult because there's a step, right? You need to actually parametrize your surface. Now, what is the surface in this case? Who knows? That was a question, not like a who knows. Does anyone know? If I drew this surface here, what would I have? If I just drew this surface, what would I mean, is there a name? Is it a plane? Guys, is everyone okay? It's like shell shock. Like, what's going on? Is everyone okay? Everyone's staring at me. Like, is it a plane? Okay, it's not a plane, right? Planes have a different type of equation. They have like, constants in front of x of y, so you add it up to equal. Okay, so what kind of a thing is it? What kind of a surface is this? Do we have any words for this, for such a surface? I'm not looking for looking for the general category. Did you say Robin Hood? Paraboloid. Okay, yeah. So the general idea here is that this is a quadric, right? It's a quadric. I mean, yeah. It's a certain type of quadric. Hyperbolic parabola, yeah. So, well, hyperboloid, I think. So this one is, if you want to go back to your old-timey notes, you'll see that this is, well, we have to bound between z equals 1 and z equals -1, right? So let's go up here, 1 and -1 or something. And what you get is you get some kind of thing like this. And it's oriented outwardly, meaning it's away from the sort of the origin. So this is our picture here. Now, if we want to orient the boundary, we get this kind of an orientation too, compatibly. So we get this picture. Now, if you wanted to actually do the surface integral here, it is doable, right? Because this, and if you were to do that, I would say, you probably want to parametrize it using cylindrical coordinates. And you could go ahead and work that out. It's something like, well, if you want, you can do something like this. Square root of 3 plus z squared, cosine theta, square root of 3 plus z squared, sine theta. Something like this. There's a parametrization of the surface if you want. Then you have to take t theta, which is a derivative with respect to theta, t z, which is this kind of uglier derivative. And you have to take their cross product. And you do that with k. It shouldn't be the worst thing in the world. Probably not too bad, but it looks like a lot of computation. Instead, let's use Stokes theorem. Right. Let's use Stokes theorem. So the first thing, if I want to use Stokes theorem, is I look at this integral and I ask, is this integrand, is this vector field the curl of something else? So is k equal to the curl of something else? Can I find a vector field where that works? This is a memory test. How many know that there is such a vector field based on memory? Nope. I and j are constants, so the curl is a type of derivative. I take a derivative of a constant, even vector fields, I'll get 0. It's a reasonable guess. Okay, everyone failed the memory test. Sorry, guys. We just did it right here. So we computed the curl here. I got 0, 0, 2. Maybe this was the hard part. I have a 2 instead of a 1, but divide by a half. So if I take this vector field f and I take a half of it, then I'll get 0, 0, 1 for its curl. Okay. Let's take A to equal 1/2 of this. So now we have that the integral we're trying to compute, s k dot ds, but this is equal to the integral of curl of A, curl of A dot ds, which by Stokes is equal to the boundary s of A. Okay. So I'm going to ask you now, because I'm just in one of those moods asking questions. What do you think this is? First of all, if I'm integrating, what does it mean, integral over the boundary of S? What is the boundary of S? It's not sort of a single connected curve, it's two. I've got, this is the boundary, this and this together are the boundary. Right? So if I wanted to actually do some kind of integral, I would have to say, okay, let's call this curve top, curve bottom. I'd have to add up those contributions. What do you think you're going to get? What? I heard something. No? It's okay. I thought I heard someone say something. That was correct. Or I misheard. Nobody? What is this? What is a vector line integral? What is a vector line integral? What we do is we take a normal vector, a unit normal vector, right? At every point. That's not normal, unit tangent vector, and we dot it with our vector field. And then we integrate that scalar function as a scalar line. That's what we do. If I look at the top and I look at the unit tangent vector of the top, I know two things. One, I know it's stuck in something parallel to the x z plane. In other words, it won't have any z component because that it's in z equals 1. So it's stuck in that plane. So that tangent vector is just in the xy plane. The other thing I know is if I go down here and I look at this kind of over the same point, it will be the same tangent vector except pointing the opposite direction. It'll be negative. So I've got an opposite orientation. When I dot that with A, again, I have no z component. I will get the same dot product, except I have a negative. One up here will dot it with A, will be the same as this except with a negative. And I'm doing a scalar integral over a circle of this, of one scalar function plus a scalar integral of another scalar function, which is a negative. So what I'm trying to tell you is that this will be this minus itself. Zero. That's it. And then I don't have to think about all that nonsense. Just use my noggin, kind of just look at it, understand it. It does take a little bit of computation just to make sure that we're over the same point x, y, regardless of what z is. I get the same dot product, but as I said, there's no z contribution to this dot product. All right, so this is very nice, very nice. And it gives us a lot of very interesting information. I can't seem to find, I'm not like a big physics person. I mean, I like physics a lot and I studied a lot, but I wouldn't say I'm a physicist by any stretch of the imagination. But it doesn't seem like there's a standard term, at least in my knowledge, of vectors that that are curls of other vectors fields. There's kind of a something close to it, which is a solenoid vector field. But well, I want to talk about such vector fields because we just looked at an example. There is a phrase for this. If I have a vector field F in 3 dimensions and it is the curl of another vector field A, we do have a name for A, so we call A a vector potential for F. It's not the same thing as a potential, scalar potential. But what we know about these types of vector fields is really kind of interesting. If this is true, if F admits any such A, and I take a surface S, and I integrate, take the vector integral, this depends only on the boundary of S. Let me explain. Oops. So we had this, we just looked at an example here where we had this surface like this. Oh, it's bad drawing. And we did the vector integral of K, which does fit into this world. The vector surface integral of K over that surface S. And what this statement is saying is really a miraculous thing. It's really amazing. It's saying, well, forget about that surface, that hyperboloid, that quadric that we just looked at. Here's another surface. Put a little handle there. Here's another surface. Let's call it S. Good luck parametrizing that, right? It's pretty rough. But now calculate this integral over that surface. It's the same, still 0 because of Stokes theorem. This is basically saying something like the surface integral is surface independent. It should evoke memories when we talked about the conservative line integral theorem and we talked about path independence. In that case, we said, let's suppose you have this type of an integral. We said this was path independent. It didn't really, it just, as long as the boundary was the same, we could have chosen a different path. We get the same integral. So one thing Stokes' theorem gives us is really a very overwhelming ability to make certain very complicated potential computations very simple. But it gives us much more. It gives us, well, it gives us our lights, for example, or at least it explains how it all works. So one of Maxwell's equations, Maxwell-Faraday equation, in electromagnetism, this follows. It says, well, the usual, you'll see that this notation more often than not. Looks like this. This, of course, is curl of E. E is an electric field. The field that is a force field that governs how, how things with electric charge move. And B is the magnetic field. Of course, these equations from Maxwell really tell us how these two fields really are the same thing. I mean, they sort of fit into the same actual four-dimensional framework. If you look at this equation, it's a partial differential equation. It's very complicated looking. Who knows? I don't know what it means. Not off the top of my head. But I know I can do something. I did when I was a kid, and I'm sure all of you guys as future engineers did it at some point. Took a wire, right? You like coiled a wire. And then you grab a magnet. Some magnet. Now magnets have this field around them, this magnetic field, so-called magnetic field. Source-free field, beautiful field. Keeps us all safe from sun's radiation, so on and so forth. Now, close to the magnet, that magnetic field's pretty strong. If I get out, I've got very small little vectors, right? Not very strong. Far enough away, I hardly detect it. If it's just sitting there, nothing's happening, right? Nothing's happening at all. So this is just zero. The change of the magnetic field is zero. Just sitting there, static. I look at that wire that I just coiled, and I just think, using my extensive imagination, I think I put some surface on it. Let that wire enclose a surface. And now I pick up my magnet and I start moving it. When I start moving it, this thing changes. I've got a derivative. I've got a change of the magnetic field over time. So I just take this thing and I move it right on through that surface. I got a big change in that field over that surface with respect to time. When I do that, I can take this beautiful differential equation, I can start thinking about it in terms of integrals. I'm almost done. Let me finish this up. I can say, well, what's really changing, because I can't understand the whole field at once, but what I can understand is the flux. The amount of field lines that are getting pushed through that surface is changing. Well, that's the integral, that's the derivative, excuse me. And we'll put a negative sign of the surface integral of the magnetic field over my surface S. Let's call this S. It's the change in the flux. I can bring in that derivative. And then I can use Maxwell's equation, Maxwell-Faraday. This is Maxwell-Faraday. Then I can apply Stokes. Let's call this wire that I coiled wire. But what is this vector integral along a curve? This is the amount of work the electric field is doing on my wire. So this is the electric work. And when that happens, electrons start moving through that wire. And we get electricity moving through our wires and turning our lights. So that's how generators work. All right, guys. So we'll finish up with the last lecture on Thursday.